Hello, everyone. My name is Hian Lam alongside Colton Peltier. Welcome to our talk, AT&T AutoClassify, Unified Multi-Head Binary Classification from Unlabeled Text. That's a lot of words, but essentially we want to extract key information from natural language unstructured text. I think how some companies are doing it nowadays is they use a closed source LLM, such as GPT-4 from OpenAI or Claude from Anthropic, to do the classification. We're all aware of how impressive these proprietary LLMs are with their ability to understand and generate text. But that performance comes with limitations, notably high cost and very long processing time. And so today, Colton and I will demonstrate how we can leverage an open source LLM to do knowledge distillation, to build and train small economical ML models with the same performance, but much cheaper cost. So on the agenda for today, we'll do a brief team introduction. We'll go into a problem statement. We'll introduce our use case, our methodology results, and conclude with key takeaways and real-world impact. So I guess I'll start. I'm Hian. I'm a senior data scientist at AT&T in the Chief Data Office. I've been here for about 3 years, and the bulk of my work recently has been in the GenAI space, namely how can we reproduce our work using proprietary models with open source models without a performance hit.
Hey everyone, my name is Colton. I'm a staff data scientist at Databricks. I work in professional services, so I partner with our customers and work hands-on to help build some cutting-edge ML stuff. So in this case, we partnered up with AT&T to build the systems you'll see here today.
Okay, so again, we'll introduce our potential use cases, dive into our practical use case that we're working on completing to production. We'll go over our previous solution that was in production about 1.5 years ago, and then how our solution is better. So AT&T has accumulated an extensive amount of natural language unstructured data. So that could span from product documentation, sales, customer transcripts, customer care, call transcripts. If we were to build a performant AI ML system, we can tap into that data to extract and act on key insights systematically, such as reducing churn, boosting sales, identifying customer sentiments, or identifying product pain points. So we have an example here. Sales call transcripts. So was there a product that the sales agent suggests to the customer? Are there certain products that the customers are excited about? What is their sentiment around those products? An example in customer care call transcripts is, did the customer ask about a certain product? Are there certain issues that the customers are complaining about? That way we can retroactively work on those problems before they become a big deal. And other text data that we have, of course, includes product documentation, user manuals, what have you. So in this particular use case we're working on customer care call transcripts. So AT&T receives over 70 million calls annually to our call centers. Those calls are recorded, transcribed, and summarized. Essentially, we want to conduct multi-label classification tasks with over 80 distinct binary categories on those transcripts. And those categories will span customer service and support issues. So some examples here is customers moving and need assistance. Customer mentions a competitor. Customer experiences Wi-Fi issues. So we have 3 examples here, but if you can imagine, there'll be 80 of those categories that we want to label yes, no, true, false for every single given transcript. These labels are important because we store them downstream, and teams that are working on churn propensity models use our outputs as features for their churn models. In this particular use case, we're able to save over 50,000 customers annually. So in our previous solution, like I mentioned in the beginning, we just use GPT-4. We use a proprietary LLM to classify each text for every desired label. So if you can imagine, we have GPT-4, we have the system prompt, so we give it the personality, we have the user prompt of the instructions we want the LLM to do. We have the summary of the transcripts, and we have the descriptions of all 80 of those labels. That's a lot of tokens to be processed, and we're expecting a lot of tokens coming out. Success factors for this use case is that it was performant enough. It met a baseline F2 score, and it was relatively easy to set up. It's just one API call for every single summary of the transcript, and we save 50,000 customers annually. But the limitations is very great, such that the cost is very, very expensive, and it takes a very long time to inference. Again, we talk about the tokens coming in and coming out. So for our optimized solution, we want you to distill a strong large language model and its ability to classify into and build training data and train that into our small classifier. So essentially, we want to have just a full transcript. So here it's a full transcript and not a summary like in the previous solution. We want to send that full transcript into the classifier and have it output yes, no, true, false predictions for every single label. Success factors here, we expect a higher F2 score because we have all of the information in the full transcript. Whereas with the summaries, it is a bit lossy. We do expect some information gets lost from the transcript to the summary. Because these classifiers are very, very small, we do expect a much lower cost and faster processing speed. Some considerations, the setup is extremely complex, and Colton will go over that. And we also start with zero labeled data. So we just have full transcripts, and we want to retrieve yes, no, true, false outputs. So in our architecture, we have two, stars. We start off with a fine-tuned embedding model, and that's going to generate embeddings for every single transcript. And then we also have individually trained classifier heads. So basically, one specialized head for every label that it was trained on. So looking at the architecture on the right-hand side, we have the full transcripts coming in. It's going to be processed by our fine-tuned embedding model, which is going to generate dense vector representations for every single transcript. And then those transcripts go into our multi-head classifier, where each head is going to predict yes, no, true, false for every given vector. And we expect the output to be a binary classification vector. Looking at the snippet of code, we have a sentence BERT model. It's going to encode the text. So here is a full transcript. We want the tensors to come back. We want to normalize the embeddings. We want the tensors to move to GPU. On the second line, we are turning off gradient calculation. And on line 3, we have the conglomerate model, which is a multi-head classifier. It's going to take the embeddings as input and output the yes, no, true, false predictions for every given label. And then I'll pass it off to Colton.
Cool. So we'll talk a bit about how do we get the data. So Hen mentioned that we're starting with a completely unlabeled data set. So we'll talk about how do we get the data. We'll talk about how we fine-tune the embedding model. How do we train the classifiers? And then how do we audit the labels and make sure that what we're getting is correct? Hen mentioned that the setup was complex for this, and that's true. And so the goal was to build a pipeline that automates that complex setup so that we can run this again and again for different corpuses of text. The really only inputs that are coming into this pipeline are your unlabeled text data and which binary labels you want to classify. And it does the rest of the work for you. So we'll start by talking about the data mining portion here. So we have a couple options here to generate the labels for this data. If we want to train an embedding model, and if we want to train classifiers, we do need labels. So one option is to do the same sort of setup that we were doing for GPT before. Right? So maybe we take every single transcript that comes in, we grab a sample of them, a few million, we grab all of our binary labels we want, and then we run through every single transcript and we classify all of them. Right? This is totally possible. You're going to have the same constraints you had on the previous inference solution, and that it's going to take a long time, it's going to be very expensive, but it's totally doable. And Llama 3.2 and 3.3 have very permissive licenses. You're allowed to reuse the data that comes out of them to train other models. So Llama is a great candidate to use here for training our smaller classifiers. But we didn't want to spend all that money, so we wanted to come up with an optimized solution. So what we did instead was we took all our transcripts, and that's what you see up there that says in documents. That is our transcripts coming in. And we embedded them into Databricks vector search. So we computed embeddings for every transcript. We put them into a vector store. And then we took all of our binary labels. These can be things like, the customer complained about Wi-Fi quality, or customer wants to upgrade their iPhone. And we use those to look up the best matches of transcripts for those labels from vector search. So essentially what we're doing here is we're passing a label in, like user wants to upgrade iPhone, and it's returning to us the transcripts of calls that are close in embedding space to that label. So we call these candidates. These are candidates for us to then go label with Llama. You can see a bit at the bottom down here how much we saved in terms of labeling. If we would have ran 3 million transcripts across 50 labels, just every single one getting labeled, it would have been 150 million labeling prompts. For us, it's kind of covered up by the text there. We ended up with about 500,000. So a big savings there. And the goal here is that we found a lot of data we can now go and label and use to train our classifiers. So let's talk a bit about what data we're actually getting with this, right? Because we're getting data that's close in embedding space to our labels. So we really want to make sure our data is representative of all the calls that are coming in. And so we've separated it into 4 quadrants here. There's positive and negative, and that's whether a label is true about a particular transcript. And then there's easy and hard. Easy means that the embedding space already has that transcript very close to the proper label. So if you look up user wants to upgrade their iPhone and a transcript comes back that immediately that's someone talking about upgrading their iPhone, that's an easy positive. That's great. But the other quadrants are important as well. We also get hard negatives. So if you look up user wants to upgrade the iPhone and a transcript comes back that's close, but it's not talking about upgrading their iPhone, that's what we're calling a hard negative. But we don't get hard positives. So these are positives that are far away in embedding space. These would be great for fine-tuning, great for training our classifiers. We also don't get easy negatives. Easy negatives are examples where it's very untrue what you're trying to look up the label about the transcript, and it's very far in embedding space. These are not coming back to us from vector search because we're just looking in the immediate area of our label. So let's talk about how we fix those 2 quadrants to sort of balance our data set here. So what I've done here is I've compressed our 768-dimension embedding vector down to two dimensions. And the white vector here represents a label, something like user wants to upgrade their iPhone. And then each of those dots is a transcript. So a green dot is a transcript where that label is true, and a red dot is a transcript where that label is false. So there's probably some negatives up there. Those are the hard negatives. There's some positives up there, which are easy positives. And actually, to get easy negatives, it's pretty easy to do. You can just multiply that white vector by -1 and just look in the other direction, right? So you should find lots of examples out here of just completely transcripts talking about something totally different than what your label was. There could be some hard positives there, but it seems unlikely. So how do we find the hard positives? So what we do is we actually look at all of our labels that we've gone through. So we get the candidates, we pass them through Llama, we get labels out at the end, and we look for the true examples we could find that are the furthest away from our vector of our label. Then what we do is we perform miniature searches in those areas. So we'll search a little bit further in that area where we found a hard positive, and we'll find more examples of hard positives. And then we'll do the same, and we sort of iterate around in the embedding space looking for more examples of hard positives. Great. So we've sort of balanced it here. We've gotten data from all 4 quadrants, and we're ready to move into fine-tuning. This is just a screenshot here of our for loop that loops through each of the labels that have been defined. And again, a label is something like user complains about some specific issue. And you can see what we have here is we go through vector search for the easy positives and hard negatives. This is a piece I haven't mentioned yet, and this is regex search. So we do allow the config file to specify regular expressions, and this allows you to do some sort of keyword search to find candidates. So you can imagine if someone says user wants to upgrade the iPhone, you might want to find all the transcripts that talk about iPhones and just go ahead and label them. So this allows you just to specify a keyword like iPhone, and it'll pull those for you. One piece you don't see here is the hard positives, and that's because we actually have to finish this step, compute all the labels, and then find the hardest positives to do those mini searches. So that actually comes later on. Cool. So we have labeled data. Let's talk about how we fine-tune the models. So we're using an SBERT model, a sentence transformer, and we're preparing our data to use cosine similarity loss. Now, cosine similarity loss is treating each label and transcript as a vector, and what we're trying to do is minimize the angular distance between those vectors if that label is true, and maximize that angular distance if that label is false. So cosine similarity is a value of 1 if the vectors are aligned, and so that's what we're trying to do is move those vectors closer together for true examples. And so you can see sort of here like what our data looks like. We have each row will have a transcript in one column, a label in another column, and then a 1 or a 0, depending whether or not we found that label to be true in our labeling process. This is an example of what the code actually looks like that's doing the training. We'd use torch distributor to distribute it across multi-GPUs. So we're using 4 A100s here to do the training. But you can see we load our sentence transformer, our loss function, our training arguments, and then we call train, which is wrapped by torch distributor. So we've got a sentence transformer trained, which is hopefully better at segmenting the space now and embedding space for making labels be close to transcripts that are true and far away for those that are false. And now we're ready to train the classifier heads themselves. So if you think about these labels we've talked about, you're going to have very different positive rates of labels, right? So a lot of users probably call in asking to upgrade iPhones. Probably not a lot call in asking about port forwarding on their modem or router, right? So those might be very low incidence of positives. You may not have as many examples, whereas iPhone examples you might have tons. So one of the benefits of training these classifiers independently is we're able to use as much data as we want for individual classifiers. So if you have lots of examples, that's awesome. If you don't have as many, that's okay. It helps us balance the data set because each classifier is completely independent. So we grab all the data, we grab the label data, and we do a hyperparameter sweep across our classifier heads as we train, and I'll show you some of the parameters we look at for that. So this is a code snippet of our hyperparameter sweep. So you can see sort of the things we're looking at. We tune for batch size, learning rate, and inside the classifiers, these are just torch classifiers, we can vary the number of layers, the dropout rate, and so on. This is all logged into MLflow as nested runs for each classifier. So you'll have, in MLflow, you'll have one run that says user wants to upgrade iPhone. You can click the expander next to it, and you'll have all of the hyperparameter tuning runs underneath, and it's easy for us to select the best one. So let's talk about this step called label auditing. So this idea is to approach something we noticed from the previous solution with GPT-4, which was there was some labels that GPT-4 got systematically wrong, right? So there's some labels where it does a great job, and there's others where it's just like maybe based on the wording we use for our label, or maybe the wording used in the transcript, it doesn't get the label quite correct. So we want to catch those and improve on that. And so what we're actually doing here is we're grabbing all of our data we used for training, and we're running it through the classifiers that we've trained. And we're looking for any place where our fine-tuned embedding model and classifier combined can still not get the right label, right? So that's what we call a discrepancy. And what we do then is we go and we do a more complex chain of thought prompting with DSPy to resolve those discrepancies. So our prompt is something like, you're a senior AT&T analyst, and you're resolving a dispute between two junior analysts who disagree on this label of this transcript. And we have DSPy dictate a concise chain of thought and then a final verdict for the label. And so this allows us to sort of iterate on the labels over time and improve them. And so here's a screenshot of what that actual inference looks like. We're using AI Query, which is a built-in Databricks function, which performs batch inference on LLMs. So we've created a column called formatted prompt that has that whole AT&T analyst thing in it. And then we use AI Query to pass it to Llama and get back the classifications with the reasoning. And we do some manual auditing of that reasoning as well. So we pull a subset of it, and you can look at it and make sure you agree with the reasoning that Llama's giving you and the change of the label. And you can see as well, you can specify things like the number of tokens that you want out. You can also do things like temperature here. If you're interested in AI Query, I'm giving a talk tomorrow on that, so come check that out. And I'll hand this back to Hen for results.
Thank you. Yeah, so we had a separate holdout test set to do our final evaluation. This test set, we used Llama 370B with chain of thought prompting, just like Colton talked about in the previous slide, to get our source of truth. So with that as our source of truth, we ran the full transcripts through GPT-4, and we saw an F2 score, an average F2 score of 0.56 for all 80 labels. Using the same transcripts in our optimized solution, we actually got an F2 score, an average F2 score of 0.79. We also observed median improvement of 24% over GPT-4, which means that any particular label that we had saw a 24% F2 improvement over the previous solution. We dug into the disagreements for the classifiers versus the source of truth, and we saw that there were very marginal percentage of disagreement for each given label. And lastly, when we say comparable complex reasoning, we found that the classifiers produce results that are similar to what a complex reasoning model would do. And lastly, key takeaways. So in our previous solution, to inference 240,000 transcripts, it took almost a whole day to do that, and we can see that it cost quite a pretty penny. But in our optimized solution, for the same number of transcripts and just 3 T4 GPUs, we were able to inference under 1 hour a day at less than $100 a month, so around 3,500 fold of cost reduction. Because of these results, we can optimize the GPUs with maybe more T4s or an A100 to do real-time inferencing. So that caps it for us. Thank you for attending. Special thanks to Databricks and Colton for solutioning this with us. It's quite been a learning journey. Thank you.